Right. Well, the interview with Hasok Chang is beginning now, and so we'll try again, see if we get it better this time. And let me first of all ask you a little bit about your idea of pluralism in HPS.
Yes, thank you. I think too much philosophical thinking about science has been governed by this idea that there is one truth about nature, that there is only one right answer to a good scientific question. And I think when we look at the actual development of science through its history, we realize that quite often science has productively worked in a more pluralistic way by having multiple systems of practice, as I put it, even within a given field. And I think science could develop even better by having a bit more pluralism in its practice. So that's the basic idea which I have been developing concerning pluralism. And this is very interesting because even if you look at someone like Thomas Kuhn, who famously put a big dent on the idea about the absolute truth that science uncovers, even Kuhn says that scientists, in order to work as scientists, must practice what he calls normal science, right, which is based upon the consensus of a scientific community to practice science in a particular way. And only through a crisis state that this given paradigm might reach, scientists will consider going into another way of doing things. And I've been trying to argue that one could really relax that kind of mode of science and say, why not have more than one paradigm in Kuhn's terms at the same time? And each will have its own particular strength, and some benefits would also come from productive interactions between different paradigms. And to add just a little brief note at a different level, I think this kind of pluralism has a lot to do with why we have such a thing as history and philosophy of science. Because if the monistic view about science is correct, in other words, if there is just one best way of doing science, and scientists certainly would know what that best way is, and in that case, there isn't really much intellectual space for people like historians and philosophers of science to be commenting on what's going on in science. I think the reason why what we do in HPS is useful is that scientists, when they focus narrowly into one direction of thinking, do miss some things out, and we can be there to point that out.
Well, now, the book you wrote, Inventing Temperature,
Yes.
Could you say something about that?
Yes, that, as you know, was my first book, and that is when I began to focus on quite basic science, if you want, basic in the sense of easy, elementary. And as you know, I had done my PhD on the philosophy of quantum mechanics, and I felt that in dealing with intricacies of modern physics, I was not able to always keep on the big philosophical question that was driving me, which was, how do we know what we know? How does science discover and establish the pieces of knowledge that it claims to have? So I thought, by going to something very simple, like how do we measure temperature, I could have an easier time of seeing my way through the philosophical debates. And it all began with a very simple question, which is shown in something like this, your normal So here you've got the 0 mark, which is where the liquid would come up when you put it in freezing water, and the 100 mark, which is where it comes when it's plunged into boiling water. This is the common sense way of making thermometers going back 200 years, right? And then you divide up the interval between the 2 points in a regular way and put numbers on the different points. And when you make a thermometer that way, what you're assuming is that the mercury or any other liquid you put in it expands regularly or linearly with real temperature. But how do you know that that assumption is true? In order to check that assumption, you'd have to have another way of measuring what the real temperature is. But that's precisely what you don't have before you've made your thermometer. So there's a very tight circularity there, which really, for me, expressed in a very clear, succinct way the nature of the basic problem of epistemology. How do we start from the state of not knowing something and get to the state of knowing something? And I couldn't figure out how this problem could be solved, philosophically thinking. So then I thought, well, at least I could look at the history and see how the actual scientists actually found out the answer to how thermometers should be graduated. And it turned out to be a very intricate problem that the great physicists of Europe argued about for more than a century. This particular one about, how we know how the thermal expansion of a liquid is regular. And it went on from there. I realized there were a host of related problems about our knowledge of temperature and heat. And that's how it became a whole book.
Well, in your second book, it was a rather intriguing title. It says, "Is water H2O?" It's saying what you had in mind here.
Yeah, that was a continuation of what I found really intriguing working on temperature, right? The most basic items of scientific knowledge, the kinds of things that we all take as common sense. In the case of temperature, I learned that something that basic had a very, very intricate and philosophically interesting history. So I thought, well, what else is like that? What about the most basic item of chemistry? Even school children of all ages know that water is H2O. Now, how do we all know that? If you take even a very clever university student in science, and if you asked that clever student, how do you know that water is H2O? They realize they've never really thought that through. They were taught to recite it, and they were taught, things like, yes, the atomic weights of hydrogen and oxygen are such and such, and you learn to figure out how to make the whole thing consistent, starting from assumptions like water is H2O, atomic weights of hydrogen and oxygen are 1 to 16, and so on. Then if you know from observation that the bulk combining weight of hydrogen and oxygen when they make water is 1 to 8, then you deduce, yes, the molecular formula of water has to be H2O. But then you ask, how do you know that the atomic weights are like that? And again, you discover yourself in a web of circularity in knowing anything. So again, I began to look at the history of how scientists actually learned that piece of knowledge, and again, it turned out to be a very, very intricate story. So another book.
Well, now you talk about phlogiston as a valid theory. Could you explain that?
Yes. So that was the focus of the first chapter of this Water H2O book. Now, phlogiston is very often invoked classic example of a piece of nonsense that scientists used to believe in and they rightly learned to discard. When I actually looked at the history of phlogiston, which is also to say the history of the chemical revolution, in which Lavoisier discovers oxygen and learns to discard phlogiston, I was amazed that it wasn't clear to me, even with the best of historical knowledge, that phlogiston was such a bad idea. So when I looked into the details of that argument, it seemed quite clear to me that by the standards that scientists usually employ in order to judge the goodness of their theories, the phlogiston theory came up quite as good as the oxygen theory, given all the things that scientists knew at the time. So then the question came up, well, in that case, why did chemists, most of them, abandon the phlogiston theory and go over to the oxygen theory? And I mean, the answer to that is quite complex and partly social. But this whole experience made me think, right, so how many other concepts must be out there which we just assume are, some outdated things scientists have learned to abandon, rightly abandon, yet really much more sensible than we normally imagine. So that's got me into a whole other direction of research in which there are many other cases.
Now, you talk quite a lot about doing your own experiments. Could you explain
Yes.
what you had in mind?
Yes. So there are two things to say about that. One is, along with the phlogiston idea, so what the phlogiston case taught me in the theoretical realm is that when you look back at past science, there are a lot of things that we've forgotten, we've lost the ability to appreciate, which used to make sense. And the same kind of thing is there on the experimental side. So when you look back at the history of science, there are a lot of claims that experimental scientists make. I say claims, but these are experimental reports, right? Things that sound very, very unlikely. And the reason I do my own experiment is to see if these things actually take place. So this all began when I was doing the research on temperature, because I was reading a lot of reports from the late 18th century and early 19th century about strange behaviors of boiling water. The reports by people like the great Gay-Lussac saying that the boiling temperature of water under the same standard pressure depended greatly on what kind of container they were using to boil the water in. And I read those reports and I thought surely that couldn't be right. And they reported even greater variations depending on how much of air and other gases would be dissolved in the water that one's trying to boil. So I thought, well, on the one hand, these things sound crazy. On the other hand, they couldn't be very difficult to check. So I got myself I got my chemistry colleagues at UCL to let me into one of their teaching labs, and I got myself set up with a Bunsen burner and different pots and pans and started boiling water, and to my astonishment, I learned that these claims from 200 years ago were absolutely true. So that was a very enlightening experience, which then led me to do a lot more work in that direction. And now, whenever I read old science, I look out for these things that sound wrong, and then very often I'm able to replicate those reports. So that's a rather long answer to your question. But the other dimension I wanted to just briefly mention is that this experience of doing experiments with my own hands, I think, makes me a different kind of philosopher, and I believe a better one. I mean, this is the best way to take yourself out of the armchair when you're doing philosophy, right? Having a direct experience of working, engaging with nature, I think it gives one a very different intuitive sense of what is involved in the business of science.
Well, now, how does Cambridge compare with UCL, where you used to work? They're
Yes.
rather different.
That's a very difficult question, actually, and I have been thinking about that quite a lot in the past 6 years since I moved to Cambridge. And I think the way I would put it is that Cambridge and UCL are, well, they're each the best of very different kinds of university. So Cambridge, of course, the traditional elite institution which can attract the very best of students, and already you can do a lot with that alone, and on top of it we have the great resources. But two things I particularly find valuable about the kind of institution Cambridge is. One is the very intensive individual attention that we are able to give to our students, even first-year undergraduates, right? And the other is the kind of very free interdisciplinary interactions that the Cambridge colleges are able to foster, which is very, very hard to do in other settings. So those two are the aspects I particularly appreciated about Cambridge. UCL, a completely different kind of institution, and I think with UCL, the very enlightened spirit of its foundation still shapes the way the place operates, the way the people there think, right? This utilitarian inspiration from Jeremy Bentham and his followers, the notion that this is a university embedded in a great city that is open to all kinds of people, whatever religion, race, later on gender, whatever economic class they may come from. And I think that public spiritedness is still there at UCL. Also the spirit of innovation, which saw UCL introduce many various subjects for the first time in the history of higher education in the United Kingdom, sometimes in the world, and actually history and philosophy of science is no exception there, going back to 1921 at UCL. So I think the spirit of innovation is still there at UCL. It's a very lively, supportive environment for someone who wants to try out something new.
Well, now, you have a fellowship at Clare Hall.
Yes.
What made you choose that?
Yes, that's an interesting question. I mean, I think when one thinks about Cambridge, often it's the great old traditional colleges that captures the public imagination, and those are great places. The reason I chose Clare Hall, which is much newer, much less traditional, is because I felt that by choosing such a less traditional college, I could have the best of both worlds, because it is a very forward-looking place within a very traditional university. And the particularly good thing about Clare Hall, even compared to the other newer and less traditional, more informal places, is its emphasis on the international visiting fellows. And I think they are really the foundation of the kind of place Clare Hall is, and that's what makes it very different from, I think, every other Cambridge college. And in my mind, that international openness really works very well with the interdisciplinary openness that's already there in all Cambridge colleges. And it's a great synergy that we can have.
Well, could I ask you finally, which philosophers and historians perhaps have influenced you most in your own work?
Yes, I've already mentioned Kuhn. I very often find myself, even when I disagree with his ideas, defining myself against him. And it's been a great intellectual and personal influence he's had on me. And then the philosophers I found most important are the ones that I feel taught me how to think outside the conventional ways of thinking that I was learning in other places. So one great example of that is Percy Bridgman. I can always remember the fresh shock of opening his Logic of Modern Physics, where it seemed that he was just absolutely committed, honestly, to ask and answer questions and see where that led him, rather than being constrained by the way he was supposed to think. In the same way, the later Wittgenstein, especially in texts like Uncertainty, and Paul Feyerabend in his self-conscious, iconoclastic ways of thinking, I don't think that always worked out as a way of doing systematic philosophy, but as a way of learning to think. Reading Feyerabend was a great thing. And then, of course, my own teachers, people who taught me in graduate school, Peter Gallison, Nancy Cartwright, John Dupre, Pat Suppies to a lesser extent because I didn't see him as often. My postdoctoral mentor, Gerald Horton, and then also many mentors that I benefited from running into along the way, even though they didn't formally teach me. So, for example, people that I met in Cambridge when I came as a visitor in 1992, yourself, of course, Jeremy Butterfield, Simon Schaffer, etc.
Well, thank you very much indeed for all those comments you make. And now the interview with Hasok Chang is ending here.